So I'll start with talking about reviewing the stuff that I talked last time. So in SUN n equal 4 superyoung people studied cohomology, fortuitous cohomologies, and so on in this theory. And one feature of this theory is that there is, if you consider infinite-N Hilbert space or operator space, then the finite-N Hilbert operator space can be understood as the quotient of infinite-N Hilbert space by space of relations. And let's call this projection map pi n. So it maps infinite-N operator, which is made of infinitely large matrices, and these are all multi-traces. And you just truncate the components, and you get finite-N operators.
This space of relation does not need to have a Hilbert space, right? It can be.
Yeah, it's a vector space. Just yeah.
Relation plus a linear combination of relations.
Yeah, but there is no need to have inner product or something.
Yeah. And using this notion, we can define two kinds of cohomologies. One is monotone, which is also called gravitons. And one is fortuitous, which is also called non-gravitons or black hole cohomologies. So the monotone cohomologies are defined as covering space. This H infinity is called covering space. Yeah.
Maybe a question.
Yeah.
So one way to define, as you said, this non-graviton is to say that they are not gravitons.
Yeah.
Right?
Yeah.
Because you have defined graviton in a certain way.
Yeah.
And then there is an additional separate definition of Fortuity. So that equality is non-trivial, right? Or one can show that this is equal.
Yeah. This is not obvious.
Okay, but it is true.
Yeah, it is true.
Wait, let me understand that. So graviton has been defined how?
Graviton is defined as infinite-N cohomology projected to finite-N.
Okay.
Yeah. So we all know this kind of
But
stuff.
I thought like that you kind of make traces and then generate everything from the traces. Let's say at least for n equals 4.
Yeah, that's what people do, and it is equivalent to doing infinite-N cohomology and then projecting it to finite-N.
Because there is no trace relation, you consider single BPS single trace BPS operators, and you just multiply them to generate multigrams.
Yeah.
So that's
In H infinity.
in H.
Yeah.
No, but then what is the second definition of fortuitous? I missed that. Fortuitous is not non-graviton. What else is fortuitous?
This Q thing.
So the definition is just independent of monotones. So it is just literally non-graviton.
No, but there is a definition, wasn't there, that states that vanish that are.
So that's a implication of this statement is that this is Q-closed using trace relation.
Okay.
But using Q-closed using trace relation doesn't mean that it is fortuitous. For example, there are some examples that you can add some graviton, let me call G, and you add some finite-N relation, which is not closed, Q-closed. Then you get something that is non-vanishing. And it is Q-closed using trace relation, but it is just graviton plus some relation. So.
But that's not fortuitous?
This is not fortuitous. This is at finite-N, this is not independent of graviton because this is just 0 at finite-N.
I see. So then it is not. I mean, I was thinking of fortuitous as being defined that way.
That's not true. This is the definition, and this alone doesn't mean.
To make that inequality non-trivial, if you define, I thought it was defined that way, and then it would not be equal.
Right.
It's okay. Yeah.
Right. There are counterexamples.
So one should not think of fortuity with this kind of definition that
right.
It becomes closed because of relations.
Right.
Because that's how Chiming explained in his talk.
Yeah, that's an intuitive way, but.
Okay.
So one feature of monotone cohomologies is that they are Q-closed at any n. So if you increase n, they are always Q-closed, but if you lower the n, some gravitons by themselves can be 0 or Q exact, so they can be lifted because the number of trace relations becomes bigger and bigger if you lower the n. So there's a higher chance of them being Q exact. On the other hand, fortuitous ones, independent of gravitons, they use Q closed. They are Q closed using trace relation. So at some point, if you increase n, they are no longer Q closed. So they develop anomalous dimension. And if you lower the Q, for the same reason here, it can become Q exact or 0. So they can be lifted or just vanish. Yeah. And this picture here is consistent with the black hole entropy plot, roughly speaking. So if you fix some integer quantized charge of the black hole entropy and plot the entropy as a function of n, when n is much greater than square root of j, it is like 1 over n. And this means that if you increase n, the number of states decrease. And this is because we can interpret this as the BPS states become non-closed for higher n. And on the other hand, if the n is much smaller than root of j, the states can be easily Q exact, so the number of states also decrease. So there's this kind of graph here. Yeah. And yeah, this.
When we're plotting these dots, is there a clear way to follow a state from one end to another?
Clear way to follow one end to another. So this is all in the multi-trace spaces. So if you write an operator in some multi-trace form, then you can, what people do is just insert n by n matrix, or n plus 1 by n plus 1 matrix, and so on. That's a sequence that we consider.
But then sometimes there are two different trace ways of writing the same state, right?
And that's why there can be some lifting or there can be some states being cubes.
Yeah, but before even the question, I'm just wondering, how do we know this state is that state? You know, when you draw these dots.
Oh, I see.
Before talking about Q cohomology,
I don't think it's very obvious.
Yeah, that's very special property of this theory. Just you write everything in terms of some n independent, n explicitly, n doesn't appear explicitly, and rewrite some operator as some trace of something like this. You just plug in n by n matrices. The point is there is no n dependence in the coefficient or the power doesn't depend on n and so on. Everything is implicitly dependent on n. So you can just follow how they change if you change n.
I think Shiraz was asking the physical meaning of
Physical
basis.
No, but I don't even know which basis, because when you're at finite-N, you can write the same state in many different trace ways, right?
Yeah.
So that's not so clear to me.
So there are many ways to write
A particular state.
particular states.
Now, how do I know then?
Oh yeah, I see. So there's an ambiguity when you consider some operator, and if you want to lift it to the covering space operator, there's an ambiguity up to this relation. And this notion, I didn't explain, but this notion holds up to that ambiguity. For example, this being Q closed using trace relation. So if you consider an operator, lifting of an fortuitous operator, this is finite-N operator and infinite. This is ambiguous. O tilde is ambiguous up to some relation. But still, this one, infinite and Q, this one is inside the relation space. And Q acting on relation is also relation. So this is also inside the relation space. So the conclusion doesn't change.
I see. So if you keep in track cohomology classes, you say.
Yeah. So there's two quotients. You quotient by Q exact, and you also quotient by this relation space. So.
And Unmu, you were saying, why do you use a basis where the coefficients are then taken to be nothing dependent domain?
No, I was, so in this SUN case, we use multi-traces as some basis. And in principle, we could choose some other type of basis, not trace, but some other complicated basis. We don't know which is more physical.
Yeah, then partially that's what I'll talk about today.
Okay.
Yeah. So in general, holographic SCFTs, 4D SCFTs, so we have typically we have bifundamental fields. So let's call this a bifundamental field, which is fundamental under first SUN. There are two SUNs now. This is fundamental index, and lower one is the anti-fundamental index of the second gauge group. And if you contract this using epsilon tensors of SUN gauge groups, this is gauge invariant because the gauge groups are SUN. And since these two indices are just different indices, you cannot decompose this to Kronecker deltas with n Kronecker deltas. If these were same gauge group indices, you can decompose this into Kronecker delta, and everything becomes multi-trace expression. But in this kind of theory, you cannot write this as some multi-trace operator. So this multi-trace covering H infinity and relation space IN is not enough. So we want something that does something similar. So I call this HB tilde, which is a covering space at baryon number B, and the space of relations at baryon number, and the baryon charge is NB, so this B is the normalized one. So the space of relations and infinite, something like infinite and baryonic Hilbert space.
I think you explained this. I'm sorry if I'm repeating the same question, but this notion of a covering space seems to be basis dependent.
Which space?
You said
Covering space?
Trace covering.
Yeah.
What is the content of multi? I mean, is it that the notion of the covering space is somehow basis dependent? You choose this multi-trace basis and then that defines your covering space.
Yeah. So, for example, you could have chosen to include determinant of x to be inside here, but we didn't. So it's a choice.
I see.
Yeah.
So the multi-trace covering, just to understand, so suppose I was a baryon number 1, multi-trace covering would be this operator and multiplied by arbitrary traces.
Multi-trace covering doesn't include this kind of operator.
Oh, it does not. It's just the zero baryon number.
Just, right.
Sorry, the baryon number is just number of A's in the...
Yeah. So this has n baryon number. If you multiply this b times, you get nb baryon number.
NB times. If you multiply this object NB times, it will...
This itself has n A's. So this itself has n baryon number. If you multiply this b times, you get nb baryon number. And there is also always some opposite charge letter. So there is minus...
B has minus 1.
Yeah, minus 1 charge, so there's minus nb and so on.
So if I take this operator now multiply arbitrarily with traces, this is some basis, which will have some relations.
Yeah, right.
Okay. Yeah.
That's what we're gonna do. Okay.
See what?
Yeah.
Right.
Yeah. This could have been some other.
Sorry, how do the trace relations look in this
a bifundamental group SUN times SUN. Can you give a small example for
Small example for trace?
SU2 times SU2?
SU times S2, example of this operator?
Trace relation.
Trace relation. That's what I'm going to explain now. So Raja should wait for a while before I explain trace relations in the baryonic space. So what I first going to do is to define H tilde B. To do that it is convenient to introduce auxiliary fermions. So let's call some. Here alpha is some index that goes from 1 to B, and P and P head is the gauge indices 1 to N. And N is some large number for now. And using this determinant of A to the B power, which is just this one to the B power, can be expressed as an integral. This is because this exponential gives this expansion, and Baryonic integral picks up the highest form, which is just MB power of this here. And because of this antisymmetry of psi's and chi's, you get something like this.
So that should have been chi there?
Chi, oh sorry. Yeah. Thank you. Yeah, so you get determinant A to B power because there are B kinds of auxiliary fermions. You get for each kind of fermion you get determinant A. Yeah, and this operator will play the role of ground state inside the space of Baryonic covering space, which is just infinite-N Baryonic Hilbert space. And the important thing is that any state in this Baryonic Hilbert space can be expressed as modifications of integral, this integral, times some mesonic traces. That doesn't change the Baryon number. So what is a modification? Let me start with some examples. Let's consider B equals to 1 case. So what is a modification of determinant A? So we have this integral. This is determinant A. and we insert some other bifundamental letter, sandwich it by these auxiliary fermions. Then this will give us n-1 factorial to the -1 power, because there are already 1 psi and 1 chi. So this gave us so we replaced one appearance of A with X. And when there are two bilinear insertions, if there are two, you replace two of these.
These are the flavors.
Yeah.
Yeah, got it. Different varieties of bifundamentals. You can take it as different things. So that's what it is.
And so on. If you insert many things, you modify these epsilon contractions. With A's, you modify it with this. Yeah.
There is no restriction on B, capital B. It can go all the way to this.
There's no restriction.
Suppose we've got 2 cross 2.
Mm-hmm.
You know, two fundamentals, two bifundamentals. So now we've got in this thing, is it right that we've got an SU2 times SU2?
Yeah.
Flavors of entry? Effectively for this construction?
Oh, you mean this B equals 2 case?
No, I meant the number of bifundamentals.
N equal
No. Yeah.
Oh.
Maybe.
A1, A2 or?
Yeah.
Yeah, I see.
If I understood right, and maybe I've understood wrong, these X's replacing A's are basically changing the flavors of the bifundamentals, right?
Yeah, they can be such examples. Yeah. For example, these I picked A1, and X can be A2. This means I'm moving inside the n/2 representation of SU2 flavor. But you can also replace it with other letters, like some
Fermions and so on.
yeah,
Say
fermions.
stick to for a moment, just the scale.
Yeah.
Then instead of looking at these modifications, I just do group theory. I keep track of the flavor representation. Is that sufficient?
Oh, so even in
Then the
chiral
traces
link,
will also have.
yeah, there are also
charges.
traces,
Okay, fine.
and there are other modifications like E.
What is B?
So there are other opposite charge bifundamental. B is P hat P.
So that would be like the traces, right? Removing a meson.
Sometimes it can be written as factored out trace, but sometimes it cannot be. Yeah, right.
Okay, thank you.
Thank you. And when sorry for using the same letters B and B, but when the number of determinants is greater than 1, you can do the same thing.
Sorry, I didn't understand that. I mean, if I have, let's just stick to A field and B field, right? And then if you have an operator, any operator which is made out of bunch of A's and bunch of B's, right? That should always be, one should be able to write it in terms of just operators of the type determinant A to the power something or determinant B to the power something times a bunch of mesons, right?
So
Whatever is the net baryon number, you have determinant to the power that, and then you have mesons. Can you not do that?
So when there are only A and B two matrices, I think that's the case.
But not.
But when there are A1, A2, and B1, B2, there are two A's, so you can consider it constructing and A2 A2,
A's
A2.
are bifundamental and B's are anti-bifundamental.
Yeah, right.
In your notation.
Yeah.
But even then, right? No.
This cannot be factorized. This one cannot be factorized. So this is just matrix product.
Oh. Ah. I see.
Yeah.
Okay, I see.
Yeah.
Like that.
Yeah, something like this.
I see.
Yeah, this one cannot be
Yeah,
factorized.
yeah, okay.
Okay, so any state is modifications, which means insertions of this kind of bilinears.
And sorry, and they cannot do that with a single guy?
Cannot do that with single guy.
Single A?
Oh, when there is just A1, when this was A1, A1, this can be factorized.
Vanishes, factorized.
Yeah, because
No, it should vanish, maybe.
this is something like
Oh, it factorizes.
yeah,
Okay.
factorized determinant
Ah.
A times trace of BA.
Okay,
Yeah.
yes, yes, right.
Yeah, and yeah, so any state is fermion bilinears times mesonic traces. Let's consider some overcomplete bases first. So let's call this overcomplete space. Span of some bilinears. Alpha 1, x1, alpha 1, beta 1, alpha m, x m, I beta m times trace of y1, w1, trace of w2, so on.
Sorry, just
Yeah.
just
Yeah.
to get oriented. Suppose I had E1, E2, B1, B2.
Mm-hmm.
First, let me look at the mesons.
Mm-hmm.
Now, the mesons transform. So I'm looking at the flavor symmetry, the SU2 times SU2.
Yeah.
Could be higher, but right now I'm looking at SU2 times SU2. SU2 is the one under which A1 is a doublet.
Yeah.
A1, A2 is a doublet, and the other one is the one under B1, B2.
Yeah.
Now, because every meson has equal number of A's and B's,
Mm-hmm. Yeah.
this tells us that mesons will transform in the J, J representation of SU2 times SU2. I mean, multi-mesons. Is that right?
So
No.
single
Because
mesons,
you have to. Single meson is half-half.
single mesons in the chiral ring are J, J.
Yeah.
So something like this, right? So these two indices can be symmetrized, or you can just contract these two with together.
Mm-hmm.
So this one is like 1,0 representation, but this is not. This is Q exact, so this is not BPS operator. BPS operators are always symmetrized indices.
Symmetrized. I see.
Yeah.
I see. So they in the end they will be in the J representation of
Yeah.
SU2.
Yeah.
SU2. Okay, excellent.
Yeah.
And now these other ones,
But that's only for single guys, right?
Yeah, single trace.
single and then you multiply.
Yeah.
I agree. Then when you multiply, you could do it.
Yeah. It could be more complicated.
More complicated. But these other these other ones are also complicated.
Yeah. Yeah. So we consider any monomial of bilinears and some monomial of traces.
And sorry, we are just discussing only the bifundamental case or also anti-bifundamental case?
So for now, I'm just fixing
these are
these.
Yeah, so we are not considering that.
So you can just shift the head to unhead ones and so on. So it's just the same thing.
I think he's considering positive Baryon number. So
Positive
ground
Baryon
state,
number.
ground states are expressed as determinant A to some power.
Okay.
But you can have B fields in some modifications.
These mesons.
Like ABA.
Yeah, exactly. So that then is not the full span, right? I mean that is not spanning. This is not spanning that.
Yeah, so my target is for fixed B.
Yeah, but even for fixed B, you are not spanning this state, right?
This.
Inside X1, Xn,
Yeah,
so X1 can be ABA.
Oh, I see. Okay.
Yeah.
X1 can be any kind of thing. I
Yeah,
see.
yeah. This X1 is just baryon number 1 letter, word, string of letters. Yeah.
I see.
So this is just overcomplete one. And
Sorry, X has to be baryon number 1?
yeah, because
This is by fundamental.
yeah, this is by fundamental.
Yeah.
Okay. So what we want is A tilde B, which is morally n equals to infinity limit of finite-N. And any operator in this space is written as some infinite integral of
See, you're looking at complex. Suppose we were looking just at a theory with only fundamental fields.
yeah.
Okay.
Mhm.
And we're trying to do this kind of decomposition, fundamental and anti-fundamental fields. That's a much simpler case than the one you're looking at.
Yeah.
And there's a simple analog of what you're doing there. And the gauge representations are only fundamental, anti-fundamental.
Yeah.
So once again, there you'll have determinants.
Sorry, what?
Once again, you'll have determinants there, right? Because you might have thought once again there that you can only make mesons, because you can have fundamental
Oh,
and
I see.
anti-fundamental. But once again, there you'll be able to have determinants.
You mean
But you'll have to do a lot of live.
Right?
Lot of live.
Oh, you mean you can't have determinants on
Yeah.
this. Yeah, right. But I was thinking that we could have derivatives and so on acting on fields.
So let's say just a single fundamental.
A single fundamental field, but then you could put as many derivatives as you want, just for the counting problem. So effectively, lots, infinite number of flavors.
Okay.
Right? This is what happens in Matter-Chen-Simons theories, for instance.
I see.
So that looks like a simpler arena to do your group. It's just probably a special case of what you're doing. I was just wondering.
Okay.
You probably have the same supersymmetry questions there, because you can make these theories supersymmetric.
Yeah.
And later we can talk about it.
Yeah, I see. Yeah. So any operator is some O integral of this O, where O is an element of this UB over complete basis. But since this is an integral, there are some integrands that can be 0. So they are just what kind of those integrals become 0 is.
What is the meaning of that infinity there? So that means many permeability variables.
Yeah. And n is formally taken to infinity.
Till n is it?
Yeah. See, alpha goes to 1 from B, but each fermions have gauge indices, fundamental and anti-fundamental. It just goes from 1 to
That
infinity.
is just A or all that span there?
A or what?
Are you taking that?
Improvements, he's asking.
Are you taking that all those guys there or just A?
So you consider any insertion
is there?
here?
Oh, I see.
Yeah.
Okay, fine.
Yeah.
That was the major factor.
Okay.
Yeah. So any element in this space is written in this form, and some of them result in the same result. O1 and O2 can be the same, and that's because there's an ward identity that this integral satisfies. So if you take derivative with respect to alpha of the integrand, let's call this S and some O. This is just 0. And you can do the same with the chi derivative.
For any O it is.
Sorry?
For any O.
For any O. But since we want gauge invariance, this O should have some gauge index P contracted.
What is e to the s?
S is this.
Okay.
Yeah.
And
So
it is 0 at strictly n tends to infinity or finite n also?
this is 0 at any n, including n equals to infinity.
And your A's are going to be allowed to be letters with derivatives. Right?
A's are gonna be A's here. I mean,
The simplest example of an A is a bifundamental letter.
yeah,
And then I could put derivatives of that
yeah,
letter.
yeah.
So it's an infinite number of A's then.
Yeah. And those are all can be understood as modifications of this thing. You replace A with some other letters.
Yeah. It's a big modification.
Yeah, it's a very big one.
So then you have to change that exponent also? With LA?
So for finite n, you don't have to do that. So you can, at most, you have to modify nb times. So you don't have to modify the action. But infinite n, I don't know. But I will project to finite n later. So it's
Infinity is a very big number.
yeah.
Usually at infinite end, this structure simplifies, right? At least ordinary gauge theory just have ring structure. Simple free ring structure.
Yeah.
Multi-particle.
Yeah.
So here there is already relation here.
So this, yeah, that's a difference. But I will show you later that there is, in some sense, multi-particle picture. Yeah. And yeah, so there's a redundancy in the elements in the UB here. And it turns out that these are everything. Any vanishing integral.
The redundancy tells you that one improvement can be related to another improvement.
Yeah.
So one bifundamental object, one replacement can be related to another.
Yes, right.
And intuitively, why was that the case, please?
Intuitively.
You said it. Okay, but mathematically you said because it was this total derivative.
Yeah.
And the action was what in this to?
This is, yeah.
Maybe you can do examples.
Yeah, let me show you some examples. Okay. So okay. So let me just finish this stuff here. So the word identity is the S times T minus S. So this insertion vanishes, and this can be expanded as a chi alpha p.
So O of course is independent of psi and chi, right?
O causes
It has no psi and chi in it.
No, it
It does.
yeah, it can have.
It
It can.
does. Yeah.
some linear span of that.
Yeah. Sorry.
Yeah. So yeah, in this case, OP is has some one less psi or chi, but yeah.
One less compared to what?
So these are all bilinears,
Yeah.
but in this expression, maybe I should have used some other expression, but this should carry one gauge index to make gauge invariant.
Oh, okay.
Yeah.
So what is M there in the span?
M here. So these are just number of bilinear insertions.
And M can be
M can be anything.
1 to up to.
Yeah.
Okay.
So this is
So the baryon charge has to be B, capital B, right?
yeah. These bilinears are neutral on the baryon number because these psi's carry baryon number -1/2. You can see this from here. This one carries baryon number 1. But it's an exponential, so. But this, yeah,
Sorry, why psi has baryon number -1
-1/2.
and x has 1.
And chi has also -1/2.
So it's total -1.
These three in total has 0 baryon number.
Oh, -half, and.
Yeah, 1.
Okay. And these trace of W are.
These are mesonic ones, baryon number 0 ones.
Okay.
Yeah.
So this equation was not there. The change in structure would have been, usually we say that the operators are generated by gauge invariants.
Mhm.
Here it would be gauge invariants and adjoints. Not adjoints, bifundamentals.
Gauge invariants and bifundamentals. Yeah, right. Insertion.
Anyways,
Yeah.
Yes, because N is infinite, so you could have many bytes.
Yeah.
No,
Yeah.
but it's still not true with this relations, I guess, right?
Right.
Yeah. They are not all independent.
Does this identity have any interpretation from the ADS side?
I don't know. So some of the excitations of baryons, these baryons correspond to some D branes wrapping topological cycles, and some excitations can be vectorized and using this identity, and those vectorized ones can be interpreted as particular excitations above the topological baryons. But I'm not sure about this identity stuff. Yeah, so this one says that when there's A with chi together, you can replace it with derivative acting on other insertions. And it turns out that every vanishing integral is of this form. So this wild identity is everything. So we have HB is equal to UB mod B, where this is the space of this kind of identities.
So let's just take OB to be psi,
Yeah.
and then you get psi chi is equal to 1.
So
Which gives you determinant A equals to determinant A.
yeah. So if you insert, if you insert A psi A chi into the
Yeah, that's something.
yeah.
But can you give us the first non-trivial?
Yeah. So let's consider A something like this. Let's consider this. So we have these together. Then we can replace this with psi derivative. Yeah. And applying this, you will get something like this derivative act on this, you get something like this. And that's, yeah.
So you're saying that if you put inside the determinant, you put ABA,
Yeah.
That's the same as having just the determinant times tracing.
Yeah.
And this should be obvious. Is it
Um,
obvious?
That's the example that you gave me.
You have
Yeah,
a
right.
maximal number of A's. They are all axis, right? So you have to factorize.
Yeah. And whenever there's A and chi together or A and psi together, you can use wide identity to eliminate them to be not directly with psi or chi. Yeah. So this space is the covering space that we were looking for. Then we need projection to finite-N by N and B. So there's
Sorry, what?
Yeah.
What can be the bilinear where this is not true, which is an independent bilinear? Psi or chi always will have some A, right?
so
Or B?
there can be
Chi and
A2s.
psi? A2,
Yeah. In that case, this doesn't factorize.
A derivative.
Yeah, right. There can be the So we have an integral with infinitely many fermions, S infinity, and some insertion F at n equals infinity. And you can just map it to finite-N integral. At finite-N.
where the F infinity to Fn is like before.
Yeah, this is just element in the UB. Yeah.
You just replace that trace by the
Yeah.
N.
Yeah. And the space of relation in B is kernel of this space. And it might seem a bit difficult to understand this space in terms of these Fermi-like integrals because there's some ambiguity and so on. But there's a nice way of understanding this space. So let's consider B equals to 1 again. Then and consider one insertion. And if we consider this system as path integral of action, Gaussian action with free fermions, this is just a correlation function. So determinant A times correlation function of the free theory with propagator A inverse. Psi P. Okay. Yeah. So this is a propagator of our theory because this is the action. So we get determinant A times trace of A inverse times X. So we can integrate out the auxiliary fermions to write it as determinant A times some trace that includes inverse. When there are two insertions, this will give this combination, because you can contract in this way or in this way. So there are two recontractions. The first one gives this double trace, and the second one gives this single trace. and so on. You can go on and on. So in this perspective, every operator in this covering space can be rewritten as determinant A to the power B times some multitrace with letter inverse included. So any relation, finite-N relation, is literally the trace relation of A inverse including. Yeah. So we now have this covering H tilde B and I N comma N B. So H tilde B projection and we have inclusion which is the same structure that we have seen before in the trace covering. And we can act Q on this space, it goes to itself. Q on this space, it goes to itself. Same here. Q is this relation maps to relation. And this the maps inclusion and projection, and one can check that these maps commute.
Sorry, before that,
yeah.
We have this different description now, right?
Yeah.
Of this infinity ring.
Yeah.
Is that the free ring?
Free ring.
Meaning you just consider these single traces with A inverse, and then you just multiply. And
oh.
Or there were these relations that you were talking about, they're taken into account already because there's A inverse?
Any wide identity is taken account already, but there is a one restriction.
A
is
inverse equal to 1.
and above that, there not any combination of.
Oh, okay.
Not any combination can occur from the family integral.
A inverse has okay.
Yeah.
Okay, I see.
Yeah.
Now this infinity problem should be easy to count using a matrix integral, right?
Yeah.
Let's do a Haar integral over un times un prime. And infinity, presumably the eigenvalues are uniformly spread over the circle.
I mean, I think if you just do it like that, then probably all the baryons will be pushed up to infinity. So here the problem has kind of combined difficulty. You have infinite operators, but you want to bring some of them down as if there is no infinity there for that sector. So it's a little, I think this matrix integral.
But suppose now I put one insertion in fundamental times fundamental. I mean, in whatever, in the baryonic thing. Well, that's just not a thing. Yeah, what I want to do is to force that there was one baryon. I can't do that by putting some Wilson line.
When there is baryonic charge, I think you can do the there's a refinement, right, of the baryonic charge. You can just do the inverse Laplace transform.
Right. No, but Abhijit's got a good point. I am forcing. Okay, I'll think. Yeah.
So let's say at infinity n, b
Yeah.
equal to 1,
Yeah.
you identify the Hilbert space.
Yeah.
Is there a way to calculate, I guess, KIAS question, the partition function over that space with the matrix integral?
Yeah. I was hoping to get a baryon by some insertion into the, what we normally do is integral u prime into letters. And let me do the following. Let me impose that the baryon charge is unity. Is n.
N. B equals 1 case.
Okay. We want infinity, right?
I want infinity. But let's say that I'll take infinity enlarged at the end. Okay. Right. So I've got un times un. and I give bifundamental fields baryon charge 1, anti-bifundamental fields baryon charge -1. So now I've got a chemical potential.
Yeah.
And I demand that the charge, the baryonic charge, is A. That should do it, in principle.
Yeah.
Now the question is whether I can simplify it that way.
No, but if the fugacities are not scaled with n, then these guys will go off to infinity in the larger limit.
Correct, correct. So I'll have to do it carefully.
Yeah.
Uh,
So scale it only on the baryon sector, not with the norm.
exactly. It's this baryon fugacity that is imposing this N charge.
No,
Right,
it's just the energy fugacity also.
Right?
There's some fugacity for energy like T, something like that. So if that is kept kind of 1 for the A, then you baryon you always have n guys, right? So it will be T to the n. You go off to infinity, right?
No, correct. Absolutely correct. So you will have to calculate energy above ground state.
There is actually one way to
Yeah.
count infinite and these kind of baryons, which was done by Jaehyeok and Lee in the giant graviton expansion paper. They counted determinant modifications of this kind. They wrote down UB integral formula. Yeah, and you can use it. Yeah.
Actually, in some simple matrix model, the bifundamental simple bifundamental matrix model, can we write down the infinite n answer for b equal to 1?
Using Jaehyeok and Lee's index.
But let's say, I mean, just take a bifundamental A matrix, bifundamental B matrix.
Mhm.
If you just have that, maybe that's just easy. But no, that is also difficult, right?
So the idea is to
I
count
just want to see how the answer looks like.
the answer looks like, how the answer looks like.
I think in that case it's probably easy because there will be just a baryon, so it will sit separately, and then there will be a bunch of mesons with the ABs, right?
Yeah. So it's like z infinity times some u1 integral, yeah, which counts the modifications by fundamental. I mean, you just have to count these insertions. Every mesonic factorial out ones are counted in this already. And you have to count this up to wild identity. And you can do that up to wild identity. You just have to subtract those that have A's that come together with psi or chi. You just have to throw those away. You can count it and you can write down some integral formula.
I see, but wouldn't the answer finally be that there is this canonical A baryon, determined A, right, times just a bunch of traces made out of AB, thought of as an adjoint field?
It can also have.
B1, A2, B2, that would be a more complicated problem.
Oh,
This AB, just AB.
just AB. I see. Then it'll be factorized, I think. Yeah.
Sorry, very basic question. You were getting 0 as a one identity, but here you are getting some non-zero also. I'm just confused.
0 and
As you were putting this equal to e raised to a as this integral.
yeah.
There was a O. This thing was O. And you are getting equal to 0, but now you are getting some answer. So
Those are derivatives.
So
I see derivative of that.
this equation can be derived using wild identity also, regarding this as psi a inverse x I. Yeah, that's right.
And this WB didn't play any role from I.
So this being equal to this uses A inverse, but there's no A inverse, explicit A inverse in the WB space. So we use the same wild identity in some sense, but these kind of relations are not in the WB space. But you can do this at any n.
So my question is to find our goal was to find this capital I space, right? N comma NB.
Mm-hmm.
Yeah. So where did we use this ambiguity? Like this played a role. Where did it play a role from?
So the point is that because of the wide identity, this might look complicated. But if you integrate out every auxiliary fermions using weak contraction, you just get determinant A times some multi-trace expressions. Then the space of relations is the space of trace relations times some determinant factor.
So WB is equal to this space of.
No. WB is also present at infinite n.
Yeah.
So this I, N, and B is finite n relation space. So these are present only at finite n. Yeah.
But I think there is qualitative difference, right? Because the structure at infinity seems complicated.
Yeah.
Unlike the previous case. And then on top of that you have these finite n relations.
Yeah.
Right?
Yeah.
It would be nice actually to write down a partition function for
Some function for
Hilbert space.
Hilbert space.
In infinite b equal to 1.
Yeah. And I think, yeah.
Or let's say A1, A2, B1, B2 model.
I think it's almost the same as giant gravity expansion. But now, since baryon is stable, there is no calculating mode. So there is no like minus sign. So in giant gravity expansion, we like subtract and add and so on, right? And here, there is no calculating mode, so I think you can use the same technique as in giant gravity expansion, but there is no minus sign. All the states will be physical.
It's difficult to make the connection. I was just thinking about this type of counting. And from there, just to see how this partition function would look like. Maybe there is a connection with giant gravity also.
Kyoto and Lee proposed their formula by using counting determinant modifications, and you can use the same formalism. Yeah.
Yeah, I think maybe.
Is it easy to write down the matrix model for? Right?
Yeah, it's actually just UB integral with the U.
UB integral.
Yeah, UB integral. There's this flavor symmetry, right? When there are B fermions, there's flavor symmetry. So everything survives the integral is the UB invariant. So
Jim,
Oh, I see. So you do the giant gradient expansion for that UB.
Yeah.
Okay.
yeah.
So it is complicated then.
Yeah, it's
Because you get this infinite kind of series, already at infinite.
yeah, already at infinite, and there are UB trace relations and so on.
Yes. Okay, fine. Okay, very complicated.
Yeah.
sorry, these are the trace relations. Is that?
So these are not trace relations. What I want to say here is that this space of relations can be understood as relations of these kind of expressions. If you integrate out fermions, everything becomes determinant A times some multi-trace. And space of relations is just space of relations of these kind of multi-trace expressions.
Some linear combination of these
Yeah.
relations. And can you give one example at the
One example.
using these?
Okay. So it's kind of hard to give one example. So
You give that example, right? ABA is equal to that kind of thing.
so that's also present in the infinite n. That when ABA becomes trace AB, that's also present in infinite n. This kind of relation is like trace relation of something like at n equals to 2. This is kind of the relation. Yeah.
So it is RHS also you can get from the path in this integral.
This one?
The RHS of this thing.
This one?
Yeah, how to get
Um,
So you just
by this combination. Yeah. Yeah.
Det A is not playing any role here in the trace relations.
A is not playing.
Determinant of A, the factor in front.
Yeah, these are just spectator. Yeah. Yeah, so we have covering structure and Q acting on each of them.
And did this guy also, I mean,
Yeah.
if I want to think of it as a 2 UN matrix integral, from that root has this been derived? In imposing the Gauss law singlet.
Oh, not counting determinant modification, just purely from
Yeah.
UN times UN integral. I don't think anybody has done that. Yeah. So we have these. If you have
The
code,
question's a clear
Yeah.
one, right? Because you impose a certain baryon number
Mhm.
and the same.
Yeah, yeah.
It's a matter of manipulating that.
Yeah.
to get that.
Yeah.
Sounds interesting.
Yeah, I think you might have to do some residue integrals inside the UN integral. Yeah. Yeah. So, okay, we have this co-chain map. So pi and I.
Sorry,
Yeah.
comment there. That clear is going to be subtle because if you did UN, you would get 0.
Oh yeah, right. It should
So
be
you
SUN.
have to know about the difference between SUN and UN.
Yeah, yeah.
So it's always subtle.
So we have co-chain at n equals to infinity, co-chain at finite-N, and this, since this projection map commutes with Q's, this is a co-chain map. This maps Q closed, Q tilde closed to Q closed, Q tilde exact, Q exact. So this is a well-defined map on the cohomology. So this map on the cohomology is called induced map, pi star, and NB. And this is a map from covering space cohomology to finite-N space cohomology at baryon number NB. And similarly, you can define iota star and B. And now we can define baryonic monotones and fortuitous. This is just elements of image of this induced map, meaning that this is a covering space cohomology, just mapped to the finite-N Hilbert space. And baryonic fortuity is just independent of baryonic monotone, which is just finite-N cohomology modified out by monotones. So these are baryonic monotone and baryonic fortuitous. So let me just give you one example of baryonic monotone in the Klebanov-Witten theory. So in the Klebanov-Witten theory, there are bifundamental fields and also same bifundamental fields in the fermion. And Q action on this fermion is like to be.
What is small?
Small a is just a bifundamental scalar.
Scalar.
Yeah. Yeah. And in the Clapeyron-Witten case, determinant A1 times A1 inverse psi B. Right? This is just an example of baryonic monotone. This determinant A factor doesn't do anything. And if you act Q on this operator, this one gives times this whole thing. And because of this inverse, this becomes trace B A2B minus trace B A2, which is 0. So this is an example of baryonic monotone that becomes Q closed without using any trace relation at infinite n. Yeah. Yeah. Okay. So we have the space of relations. And since this is just determinant factor times multitrace relations, this satisfies this relation. So if you increase n, the space of relations becomes smaller. And because of this, if you have a if some cohomology, baryonic monotone cohomology is, so this is a representative of the covering space cohomology. And project it to finite-N space. And if this is not exact at n equals to n1, then this is also not exact at n for greater n. The space of relations becomes smaller. So monotone becomes more difficult to become Q-exact. So higher n, they become non-exact. Once, yeah?
Sorry, more difficult or impossible?
Impossible. Yeah. It was impossible at smaller n, so it is more impossible at larger n. Yeah. And yeah, the same is true for fortuitous cohomologies also. If it is not exact at smaller n, larger n, it is not exact. So we can draw the same diagram. Numerous dimension, so monotone, baryonic. The anomalous dimension should be, at lower n it might be Q-exact, but at some point it should be just BPS and stay the same. And we also draw the same diagram for baryonic fortuitous. It can be exact at lower n, but it can be non-closed at higher n. So same phenomenon happens. Yeah. And we have defined baryonic fortuity and monotonicity. And since we focused on fixed B sector, in the paper we generalized to non-baryonic cases too. So for example, if you multiply determinant A and determinant B, this is baryon number 0. And this decomposes into multitraces. But you can similarly consider extending the covering space as where this 0 and 1 means there's no determinant here, and there's one determinant factor here, and so on. Using the auxiliary Fermion formalism, you can do all the same things.
I didn't understand. So you fixed B, and then further you are grading that space?
I'm
So
extending.
let's say B equal to 1,
Yeah.
and then what?
I'm extending this. This is the baryonic space that we considered, and I'm extending it by considering determinant AB inside the covering space. Determinant AB
But that's already in there.
already in. So at n equals to infinity, there is no determinant AB. Yeah,
That's what you're saying.
yeah,
I
right.
see. So you want to bring some of them down.
Yeah.
Oh, okay. I see.
Yeah. To consider products of cohomologies, we naturally have to do this kind of thing. And yeah,
Sorry, is there some other feature that is there in this particular problem where you have baryons? Then the one we, like for the SUN n equal to 4 superangles, is there some different feature than the one we encounter in that case?
Yeah, like what is the presence of Baryon giving us? We are getting the same graph.
what is different feature except for the existence of baryons? You mean baryons, do they behave different from the?
Because this kind of graph was also there, this monotone and fortuity.
Yeah.
Was there as well.
Yeah,
is
one-
there something else we encounter in this particular problem, or what is different here?
So difference is that if you increase n, baryonic states have increasing energy along the n. So they are different for each n. In fact,
Yes.
they have different energy and charges for each n.
But isn't that the case there as
In the trace case,
yes?
everything was trace. If you increase n, energy will stay the same. Just the size of the matrix becomes bigger.
XY will remain, the energy will remain same.
Yeah.
even if- Okay.
Yeah.
But here it will
Yeah, we're-
change.
We are increasing n and energy at the same order.
And can we use that thing to fortuity much better? Is that what we're saying?
So my point is that you need, in the more general holographic setups, you have baryons, and you have to deal with baryons. And there's a similar classification for those baryons as monotone and fortuitous.
Are there black holes in this Klebanov setup that have baryon charge?
So in the,
Supersymmetric black.
you mean gravity side?
Yeah.
I think some people, I heard some people talk about baryonically charged black holes, but yeah, I'm not sure.
So it won't be the black hole solution with some brain wrap
Um,
around S3?
yeah, I think it could also be possible. But black holes might also have some,
You might have more. You might have order n square baryon charge.
yeah.
It doesn't become a supergravity solution.
You mean order n baryon charge?
Yeah.
Oh,
So-
NB is n squared. I see.
Yeah.
Yeah.
So the n squared is bifurcated. Yeah.
So that's the kind of barrier. You want a microscopic barrier.
Yeah, something. That would be somehow very new.
Oh, I see.
Yeah.
At least from the filter side, if you find the saddle from UN or SUN, the result string is almost the same. UN theory does not have baryons. I don't know. Yeah.
But if you,
You have
yeah,
to find the field, the saddle after imposing the baryon charge.
yeah,
So it's a new kind of saddle.
Yeah.
yeah. Baryon number is just wrapping number in the 3 cycle, right? So maybe baryonic black hole should be wrapping 3 cycles, I guess. I don't know.
This, I've forgotten this Kerr number. 3 cycles part of the internal manifold?
Yeah, internal manifold. Yeah.
Right. So it will be wrapping that. But if you look at it just from the ADS point of view, that will be just some other gauge field charge, right?
Yeah.
So there will be some supersymmetric black hole from the ADS point of view that is another charge field, gauge
Yeah.
field turned on.
Yeah.
And what's not clear to me is this, that this baryon charge, we call it n square, but in some sense it's actually n, right?
Yeah.
Because it's n times. So from that point of view, you might think it's too little to affect things. On the other hand, you've got this large growth of this other stuff.
Sorry, but N branes, right? N branes.
N branes.
That's-
That's energy n square.
Yeah.
But it's not n square different things.
I see. But if you take N square to entropy.
Yeah. But on the other hand, you've got some large stuff happening here. So because you're changing singlets to bifundamentals, and maybe that's in itself enough. But that counting is not clear in my head. Whether that's enough to change the nature.
If you want to view a black hole as a degree balances, then it makes sense to just n number of baryons
N number of variables. I think the question is that then will there be, which for such a black hole will it have a macroscopic area? Yeah, if they do, that's very interesting, right? That's completely new.
Yeah.
It's not some small modification of the old model.
Yeah.
In N equals 4, I think that's what you were trying to relate. I mean, the giant graviton expansion. You have the giant graviton expansion, and in some sense, the n square energy states. You just n giant gravitons.
Right.
So that interpretation.
Right, that
can
suggests
get
that
us.
it should be, yeah,
But
absolutely.
you don't have that detection using baryon charge.
Right.
Yeah,
Right.
yeah. No, it's a good point. So this suggests that it should be.
Yeah.
It should be macroscopic, I agree.
Yeah.
But as you were saying, I mean, if you thought of it from the point of view of the matrix model, it looks like a completely different kind of satellite. Because it's one that is there in SUN but not in UN. It's one where somehow it's very different. This shouldn't be like a small black hole limit where it's like nothing's happening.
Yeah.
So it's somehow different. And so for that reason, very interesting, right?
Yeah.
So the question, what about the index?
What about the index?
The index in this model, is it clear that the index has all n square states?
At fixed baryon charge.
Fixed if necessarily large. But to get something different from matter.
So I
Has
think
that been looked at? That looks like the first natural equation, right? And before looking at Fortuity, just to look at the index.
I think it's not directly considered so far.
That looks like an interesting question.
It's
Yeah.
hard to see because we don't know the integral formula for finite-N.
Really?
At finite, so we don't know how. So I mentioned that we can obtain some finite baryon contribution to the index by considering giant graviton type.
Oh, yeah.
Giant graviton expansion type of formula, which is valid in infinite-N.
And it counts only baryonic monotones.
No, but the first thing I would do is just look at the UN times UN integral.
Yeah.
Look at that series.
Yeah.
SUN times SUN.
I mean, as a toy model, reproduce whatever you're supposed to get for this infinite n problem from that.
Yeah.
And then seriously look at the index.
Yeah. Yeah.
I mean, that's an exact thing.
Yeah.
Yeah.
So that last analysis of the index, one can use this modularity and all that, right? So that should just work to give you the entropy.
Yeah.
Right?
Yeah.
For any gauge theory, pretty much.
So using Gayatolli's and giant graviton formula,
Is this the same as the Carby formula?
Yeah, the Carby type formula.
So it comes from the C minus A?
I don't Yeah, there is we have some C and A.
C minus A, right? It's the thing that for n equals 4, evaluate, it gave a difficult result. You couldn't say much for it. This Kumar-Gotsky stuff, like 10 years ago, that's good.
No, but you might also use this kind of modularity, right?
If you
And then
use second sheet, then you will get 3C minus 2A,
Which is something else. I see. So C and A.
yeah, C and A.
Okay, now how do you get the baryon charge into that?
Now this will be true even for U theories, UN theories.
U theories.
So it's like a zero baryon.
Right.
It already has black hole.
Good.
Now you want to see.
I want to see something new with the baryon. So
Yeah.
maybe there's some anomaly associated with the gauge field that comes to baryon charge. Like this.
Yeah. Yeah, that's a good question. That's a good question. Yeah. Yeah, the anomaly then should go on some.
Anomaly in the field theory.
And the field theory. Yeah. C and A are anomalies or something. Right?
I don't have good answer right now. Yeah. Okay.
Different B sectors can they mix as well?
Different big sectors are different charge sectors. Their quantum numbers are different, so they cannot mix.
They can't mix.
Yeah.
Mix meaning what?
As in these Qs don't come.
U has zero variation.
So it commutes with B.
Yeah.
But there is no operator which doesn't commute with.
There can be operator. The operator is non-zero variant.
Okay. So let's talk about the Klebanov-Witten theory specifically. Just to recap.
One last comment.
Yeah.
The fact that in ABJM, very roughly speaking, the analog of the baryons are the monopoles.
Yeah.
And Jaehyeok was so beautifully able to compute the index of that.
Yeah.
If we were doing SUN rather than UN kind of theory,
Then
it would
is
be like baryons.
yeah.
Right? So feels.
But wasn't it the case in Silk's computation that for large N only zero monotone contributed or something like that? I don't remember the paper now.
No,
In large N there was some simplification.
Large N at finite charge simplification. Right? It's just like, okay, sorry,
But he was able to compute for large charge also.
large.
This large, I think this large charge computation was for, as just mentioned, for finite energy. So if you want to mimic his
This Klebanov-Witten theory has the same superpotential as the ABJM theory and same quiver structure. So the baryonic monotone of this form, which are purely made of bifundamentals, also present in the ABJM theory, except that this one is not gauge invariant in the ABJM theory. But if you multiply this with opposite baryon charge, then you get some operator that behaves monotone. But so the story is that in people consider ABJM cohomology problem, and they found fortuitous cohomologies, non-graviton cohomologies at very low energy, and it turns out that they are of the form this determinant A modification times determinant B modification. Yeah, it can be written in that form.
But in your language, are they monotone or fortuitous?
They are generalized monotone that are non-gravitons.
Meaning the way you find it now with the abstract definition.
Yeah. They are cohomology in the covering space with determinants
Yeah.
projected down to finite-N.
Okay.
Yeah. Okay. So we have SUN times SUN, two bifundamentals, A1, A2, two bifundamentals, B1, B2, and superpotential is lambda trace of 1, B1, B2, minus A1, B2, A2, B1. And this is a strongly coupled theory. We don't know the IR Lagrangian, we just know the UV Lagrangian. And so since we don't know IR Lagrangian, we cannot really consider IR cohomology. We have to just use UV Lagrangian and derive Q action from the UV Lagrangian, classical Q action, and do the similar thing in the case of n equal 4 families. And yeah, so since this is a UV, since this is a UV Lagrangian cohomology, there can be quantum corrections that lift those classical cohomologies of the UV theory. UV plus mass. So what we do is just find classical cohomologies in the UV plus mass, and we just try to explain the index. If some operator is not guaranteed to exist by the index, they might be lifted or not. Okay.
Well, sorry, so you can do a mass definition that preserves the index.
Yeah. So let me explain more concretely. So this Kleban-Witten theory can be understood as flowing from SUN times SUN n equals 2 or before theory. With two bifundamentals. Two bifundamentals.
This is the order for the n equals 4.
Yeah. So it's C2 more Z2 times C. And this theory has superpotential Jaehyeok times some adjoint. So this is n equal 2. So this is adjoint chiral scalars, chiral multiple, plus trace this superpotential, and we deform this with massive superpotential. We give mass to these adjoint chirals. And in the IR, these are very heavy. You integrate out these adjoint chirals. Then you can just plug the equation motion, and this IR superpotential becomes Yeah, yeah. And this becomes this. And this theory with mass deformation plus the conical theory.
Sorry, M here is just 1, 2, right?
M here?
No, that's the subscript.
Oh, this is 1, 2. Yeah.
This capital M is coupling constant.
This is just mass of the adjoint chirals, adjoint chiral multiplets.
Oh, so this is what you were talking about with mass, you're saying?
Yeah, yeah.
Okay.
Yeah.
But I thought you were going to further mass deform this theory.
Oh, no.
Okay.
We don't have Lagrangian of this theory, so we just work with this theory, massive theory.
Got it.
Delta W is not a small perturbation. It is
This is not small in the IR.
not small in that.
Yeah. It flows to a totally different theory.
Oh,
So, Jaehyeok, I mean, if you do this calculation in that case, with
Yeah.
mass,
Yeah.
and you do the calculation here, assuming lambda is small,
Mm-hmm.
would they not be the same?
Oh, you mean mass is large, so this is small?
No, I'm just wondering, I mean, if you do cohomology calculation
Mhm.
with this theory,
Mm-hmm.
with mass present,
Mm-hmm.
and in that theory,
Mm-hmm.
both calculations are done at tree level,
Mm-hmm.
would you get the same answer? I'm saying integrating out should commute with taking cohomology.
So
Is it just quadratic it out?
yeah, the thing is that we obtained conical theory in this way, but you can also obtain conical theory using this quiver with scalar potential, standard scalar potential, right? Some standard scalar potential. This is not CFT. This flows to the conical
No, I
theory.
agree, but I can do a calculation, right? I can just
Yeah,
take,
yeah.
I can just write down Q, assuming this lambda is small,
Yeah.
and then write down the Q action.
So
Formally, I can define something.
in the Q action, you need scalar potential. You need scalar potential and derivatives of them, because we have to use initial Q action.
But if I don't do any of that, I just take this superpotential.
So for example,
Lambda will have a mass scale of that, right? Because these A's, if you thought of it as roughly weakly coupled, all these ABs would be dimension 1.
yeah.
And then the potential of the theory is like dimension 6.
Yeah, this lambda has dimension of this one. And yeah, what?
Somehow the anomalous dimension is somehow key to making this work, right?
Yeah,
It wouldn't be conformal otherwise.
yeah. In the IR, this is exactly marginal because these have anomalous dimension. Yeah, and when you have to use Q action, there's, for example, if you act Q.
Even there, so
Yeah.
even there is mass, right? Mass scale there.
Yeah, there we have to keep mass scale because we are dealing with UV Lagrangian.
Yeah.
Yeah.
Roughly speaking, the kind of equations you will get is Q1 psi is equal to phi, right? It's going to make phi exact with the mass. So you just deal with that.
Yeah, you're saying if you're integrating out
Yeah.
the massive field gives you that, then
Yeah,
it's the same thing.
Exactly. It should be the same, right? The level
you're
of
just doing one.
cohomology, the tree level cohomology
Yeah.
that I write down.
Yeah.
Should it, because it's just saying that phi is exact.
Yeah, I think you're right. That because you're getting that by integrating this out, right?
Yeah. I mean, if it was a complicated thing, it's just quadratic thing, right?
Yeah.
It's just setting it directly to exact. So I just dropped that in the beginning itself.
Yeah, I think you're right.
Yeah, so that's possible,
Okay.
but you have to use this scalar potential to derive the Q action, and you get the Q action, and it turns out that even if you use this theory, and you can argue that doing some sort of coordinate transformation of fields, you can arrive at this Q action by cohomologically integrating out these
Right,
adjoint
that's what I
chirals.
was saying, but I didn't have any Keller potential in mind. I thought it just happened.
Yeah, and it can be done. Yeah.
without the Kähler potential.
Yeah.
As this mass preserves some part of the index.
Mass preserves, mass, sorry, so mass doesn't preserve the index. Mass deformation means that these adjoint chirals have 0 index, right?
So there were these flows, right? There were sometimes flows that preserve some part of the index, like this Rommelsberger flow.
Oh, I see. So, yeah,
Is this of that form?
yeah.
So you could compute the index just from this sigma z2 theory.
Yeah.
No, I mean,
You don't even have to consider this. You can just start with this and compute the index. But you can also consider this theory, and these adjoint chirals are extra ingredients that have 0 index. So
yeah, exactly. Both will be there. Depends only on the R charge.
yeah. But and you can do the similar thing in the cohomology sense. These adjoint chirals become if you write down some Q cohomology with these adjoint chirals, you can show that they are always Q exact using some Q action in the Lagrangian. So you can just deal with these letters without adjoint chiral. Yeah. So that's what we did, and yeah.
So now you'll be talking about non-baryon Fortuity.
Yeah. So, let me just show you the examples of the cohomologies. So these are chiral scalars, and I'll call small a and small b as the antichiral scalars. They are Q cohomology of the BPS letters of my chosen supercharge. Then this one is one of the gravitons. This is Q close non-exact. And this one, AI, B. This is also a graviton. You can increase the number of A, B, and so on. And the flavor indices are all symmetrized. So they form a tower of gravitons that are in the K over 2, K over 2 representation of SU2. This says SU2 times SU2 flavor symmetry. So this is the representation. This is an example of a graviton. And there are other gravitons like this is also a graviton. So here psi A is chiralino corresponding to the A chiral multiplet. And there's also other gravitons and so on. So we have many towers of these gravitons. And in n equals 2 case, we studied the cohomology problem, and in that case, I just show you some baryonic monotones. So of course there are determinant of A. And determinant of B. And there's also this kind of baryonic operators. And there's also one with field strength. There are two kinds of field strengths because there are two gauge nodes.
Why we are calling them as graviton?
Just a second. Sorry, what?
Why they are graviton?
So these are generalized monotones, baryonic monotones.
Monotones, okay.
Yeah. At n equals 2. So there are 2 letters inside them. Yeah. And we counted, we worked in the so-called BMN sector, which is just a sector that exists only in the classical cohomology problem, which simplified the problem. And we counted gravitons and generalized monotones. And what we found is that the following. Okay. So we counted these gravitons and subtracted from the BMN sector index. We computed index and subtracted. Plus baryonic monotone n equals 2. Then we get where this index is trace of minus 1 to the f, e to the, which is equal to delta plus G1 for some convention. So we get some non-graviton stuff, non-graviton, non-baryonic monotone stuff at t to the 30th power. In n equal 4 parameters with gauge group SU2 and SU3, it was like t to the 24th power. We have a little bit higher energy. And
Wait, this was in the 0 baryon sector?
so this includes everything, including this kind of thing, baryons. And at n equals to infinity, n equals 2, the symmetry, the global symmetry was SU2 times U1 baryon, and it enhances to SU4 at n equals 2, because the superpotential becomes determinant of the scalars. It can be compactly written as some one scalar. And this 35 is the dimension of totally symmetric rank 4 index of SU4. So this is 4,0,0 as a thinking label of SU4. And this includes all the baryonic states and mesonic states and so on.
How do we decompose the 2 to 1?
In this. So we have found this operator in 4,0,0, have I, J, K, L indices. They are all totally symmetric. And baryonic symmetry acts on 1, 2 index as positive, 3, 4 index as minus. So if you consider component like 1, 1, 1, 1, this is baryon number 4. And if you consider
Number
yeah.
0. Oh no, 1, 1, 1. Okay.
Yeah, 1, 1, 1. And 1, 1, 3, 3 has baryon number 0 and so on. Yeah, it is. We found some explicit expression. It's quite lengthy to write down. It's like lengthy, not as lengthy as SU3 example, but is much lengthier than SU2 example. And one thing that we did is we checked this is Q-close using some ansatz, and we checked that this is non-exact using some maps to the n equal 4 spectrums. So there is a truncation from Baryonic theory, so n equal 4 theory. So this is just this is this is a map that turns off some of the fields of Klebanov-Witten theory. And it turns out that the Q cohomology of Klebanov-Witten theory maps to Q cohomology of n equal 4 theory under that truncation. So this is a this thing holds.
Sorry, I didn't understand this.
Yeah.
What is this? So you have cohomology.
So let me
Different theories, right? What is the map?
let me explain in more detail. So just a second. Okay.
I mean, is it basically the untwisted sectors?
Untwisted sectors.
Meaning, if you think of it as coming from an orbifold, then the orbifold will have twisted sectors and untwisted sectors. And the untwisted sectors are how a sect.
So it's more like Higgsing. So Klebanov-Witten theory has 4 fields and 4 chiral scalars. And if you pick these to be proportional to the identity, then the gauge group becomes SUN that preserves the identity. Then one of these 4 matrices become Higgs in the IR, in this vacuum. Then you get 3 matrices. And n equal 4 spangments has 3 chiral scalars. And these 3 matrices play the role of 3 matrices of n equal 4 spangments.
Sorry.
This is so weird. What is this concept?
Yeah.
Meaning A is bifundamental, B is anti-bifundamental. How is everything happening, becoming adjoint?
But you're Higgsing.
Oh, you're using I see.
Yeah.
Identity.
Sorry for I'm rushing too much.
Expansion value, which is identity.
Yeah.
It locks.
Yeah. You set the web to be identity, proportional to identity, then the gauge group is broken to SUN, and the bifundamentals act like adjoint of SUN. And yeah, those are X, Y, Z of the n equal 4 spangments. And you can do this for all other cohomology letters, BPS letters. And it turns out that truncation can be shown to be consistent truncation. And it maps Q close ones to Q close ones and Q exact ones to Q exact ones under that truncation. Yeah.
So it gets in particular a marginal parameter, exact marginal parameter in the IR.
Marginal parameter in
Because
there.
it becomes n equals 4, you're saying.
Yeah, there's an enhancement of the symmetry. And marginal parameter was already present in the Klebanov-Witten theory. Actually, yeah.
Okay,
Yeah.
I guess there are maybe marginal parameters, yes.
Yeah, that map is a little bit.
Sorry, I mean just naively, if I set one of the B's to 1 and the superpotential, I get n equals 4 superpotential.
Yeah. So originally we have this one, and let's just pick B to be identity, and everything else to be 0. Then you have this to be B, this is B, and we get A1 times commutator of B1, B2. Sorry, B1, A2, I think. Yeah. B1, A2, and yeah, that's the superpotential of the n equals subcameras. Yeah, and using this map that we have found, this operator under this truncation map, this becomes proportional to O0 of the SU2 SU2 n equal 4 parameters, which is the lightest threshold level fortuitous cohomology that people have found.
But that's T to the 24, right?
The thing is that there is some component. The wave comes here.
It breaks it
Yeah,
down.
yeah.
I see.
The
goes lower.
yeah, it goes lower.
Smaller symmetric group.
Yeah.
Because you can't mix all four.
Yeah.
It's like SU4 goes to SU3 or something like that.
Yeah. SU4 becomes SU3.
Yeah.
So this kind of thing was studied in the
Must have been. I'm just thinking about it in the following language. That the original parent n equals 2 theory was obtained by putting the branes on top of each other and then doing a C2 mod Z2 orbifold in the internal space, right? So there should be some part of it that is like an untwisted set. This is just inherited from the parent theory. And I was wondering whether that is in some language. You know what I mean?
Yeah.
So I was wondering if somehow, I'm sure it was.
Somehow not this.
Yeah.
Even this construction was not familiar. But I feel there's some language in which it may have been. But,
Will you get new trace relation after the truncation, or I can just put identity in the old trace relations?
Trace relation.
Right, from going from there to here.
Going from
You have
here
some
to there.
trace relation there as well.
So there are trace relations here, and truncation map is literally turning off some fields components.
Yeah,
So trace relation maps to trace relations.
I see.
Yeah.
Sorry, in tangential question, if I write down the index of this, there is some way of giving the wave at the level of the index, right?
Oh, I don't know. So you have to be able to isolate some vacuum, right? How can you do that?
Yeah, maybe people do that for symmetries, I guess, some moment map. Like UG does this kind of thing, but maybe not for a field.
I see. Yeah. So we have found this operator, and it turns out that if you multiply this with some gravitons that I call U, which are just chiral scalars, and this whole thing totally symmetrized. This is in the representation 4 plus 2n, 0, 0. And this also maps to O0. Yeah. So we have found more Q-closed and non-exact operators. Yeah. And you can also dress with some other graviton and yeah.
So you have found a form of the T as a matrix?
T?
Yes.
T is T as a matrix. T is a map from here to here, and you have some operator here. You just turn off some of the components of the field, then they become N-4 map operator.
This operator equation T acting on this thing.
Yeah.
What is T here?
So you have this specific operator in the Klebanov-Witten theory. You turn off some components.
Okay.
Yeah.
By identity, just identity, putting them identity.
You just turn some of the components to 0, and you get this.
Does this suggest at all that this cohomology calculation is exact?
Oh.
why?
Because you do two flows and you get
You're saying this one loop cohomology.
One loop, yeah, one loop cohomology.
What are the two flows?
From n equals 4 to this Klebanov-Witten, and from there to again n equals 4 apparently from the evening. And then you get the answer for n equals 4.
N equals 4 orbifolded to Klebanov.
Yeah.
Yeah.
One possibility is that in the beginning you don't really go and do the exact calculations. You kind of skip that step and then directly get n equals 4. So I don't know the evidence is either for non-exactness or exactness.
Sorry, what is this statement?
No, I was just wondering whether this is suggesting that, there has been a lot of discussion about whether one loop cohomology is exact or there are corrections and so on, right?
Yeah.
N equals 4, for example, and we do believe when RG flow happens, a lot of things change, right? So, because this example is suggesting that you start with N equals 4, then you go to this Clifton-Overton theory, right? And then you do a further flow, again N equals 4, by Higgsing this B2. And then you are getting the tree level answer for N equals 4.
Yeah.
So, I don't know, maybe it doesn't suggest anything about the intermediate calculus.
Isn't this last paper by Jaehyeok making it clear that N equals 4 is not, one loop is not exact?
One loop is not exact.
Even in N
Yeah.
equals
N equals 4.
But I thought his question was about the robustness of this Kleber-Witten cohomology.
But I mean, if the evidence that is that it maps to one loop and N equals 4, but that is not exact.
I thought you were saying one loop, your one loop and your one loop were different.
I think the same.
Same?
Yeah. I mean, the purist argument would be that there shouldn't be any match once you go down, right? It is matching at tree level anyway.
Yeah, you're saying one loop seems very robust even if it's wrong.
O0 is not lifted. Yeah, so
Yeah, maybe.
Maybe.
Not, maybe.
yeah. And this
Sorry, maybe there is no evidence either way.
yeah.
So then what? I mean, if it's not working for N equals 4, should I take it that this is generally will not
I
work?
think it'll never work. If it doesn't work for N equals 4, why will it?
Right.
My feeling. Because I had thought somehow mystically that N equals 4 is such a great theory that should.
But we had, again some tangential comment, we had this example of trialities in two-dimensional 0, 2 theories, where you start with gauge theories, 3 types of gauge theories. And not only do we argue that they are dual to each other, but we also say what the infrared theory should be. And it's manifestly symmetric in all these things. Right? So then, if that really is correct, then the proposal is that it matches and it matches to that Kazama-Suzuki cosine model in the IR. I think that might be a good test bed to
You're saying do it in that case.
do it in that case. And then you actually have infrared. Like a proposal.
Nice.
If it's not working for N equals, it seems strange that it will work there, but maybe. Sorry.
Yeah, that's it for my talk. Yeah, thank you for listening.
Why you were matching here with the untwisted sector?
You know, when you do an orbifold, you get some new things, but you also get some old things. So the old thing, so before doing the orbifold was N equals 4. So the old thing should feel like N equals 4. Right? So the untwisted sector had some N equals 4 flavor. That's basically what it is.
So that symmetry should match with this Higgs symmetry.
I can't see any of the details. I was just saying that there is some reason you should expect some part of it should look like N equals 4 because it is restricted to the untwisted sector. But I can't see how that matches to the way you do it. So maybe it's different.
In the orbifold theory, maybe you can do the same Higgsing by choosing some identity vacuum. I don't know.
But is that in any sense going back to the parent N equals 4? The Higgsing, I can't understand this one.
And in the conifold geometry, what is happening?
So conifold, you have this,
Yeah.
and you just pick one vacuum here and flow to the IR.
Yeah.
It looks like C3.
So it's like going to that bunch. Yeah.
Yeah.
Okay, so
Go away
it's
and then just.
Yeah.
So this then must be a very generic phenomenon. You start with any orbifold, Higgs it and it start looking like N equals 4.
Right. Any YPQ
So
is
everything is C3.
Yeah.
Away from the orbifold point. Okay.
very
Thank you.